This video will be the single most important lesson in this entire course. Maxwell's laws heavily summarize many concepts we have seen so far. The laws are a collection of 4 equations. We will explore them qualitatively, one at a time. To begin, let's revisit a concept we explored a few videos ago, the concept of magnetic flux. Magnetic flux is calculated as magnetic field times area times an orientation factor. It is a way of measuring the amount of field, the number of field lines passing through a certain area. In this visualization, we treat the area as something flat, like a sheet of paper. But we could also curve or fold the paper so that instead of being flat, it encloses some space. This way, there's a clear inside and outside, and the paper completely separates them. In this sort of geometry, the boundary is called a Gaussian surface. It's a hollow skin that totally encloses some space, so there's no communication between the inside and the outside at all. We see Gaussian surfaces in everyday life. In this picture, we see an empty glass sphere. Because it is totally closed, we can consider this to be a Gaussian surface. Now, let's look at the sunlight in this picture. Even if we didn't know how much light was entering the sphere, there is one thing we would know for certain. All the sunlight entering the sphere passes through. Since none of the sunlight gets trapped in the sphere, and since there's no light source within the sphere, the amount of light entering the sphere must equal the amount of light exiting it. Something similar applies for a Gaussian surface in an electric field. For this Gaussian surface shown in green, the total electric flux entering will be equal to the total electric flux leaving. Now, going back to the glass sphere analogy, there is one way that more light can exit the sphere than enters, and that is if there is a light bulb inside the sphere. Similarly, the only way for there to be more electric flux out of the Gaussian surface than entering is if the Gaussian surface physically contains a proton, or at least more protons than electrons. Vice versa, if the Gaussian surface contained more electrons than protons, there would be more electric flux in than out. But if the number of protons and electrons are balanced, then you would once again have a balance between the flux in and the flux out. If we express this as an equation, we would write it like this. This is Gauss's law for electric fields. It says, if there is a net charge enclosed within the Gaussian surface, either more protons than electrons or vice versa, then there will be an imbalance between the field lines out and the field lines in. Otherwise, if no net charge is enclosed, flux out and flux in will be equal. Importantly, notice that epsilon 0. That's called the permittivity of free space. We last saw that variable a few weeks ago when we were talking about capacitors. It will play a major role here. The second of Maxwell's laws is one we've seen before. It's Ampere's law with a slight tweak. Ampere's law says that an electric current produces a magnetic field. Maxwell interpreted this a little differently. An electric current is made of moving electrons, and each electron creates its own electric field. And of course, if an electron moves, its electric field must move with it. So another way to phrase Ampere's law is to say a moving electric field creates a magnetic field. Now, the only issue here is that Ampere's law in its original form made an assumption. It assumed the current was constant. Maxwell adjusted Ampere's law to account for the possibility that the current isn't constant, that's represented by everything after the plus sign. In that case, we get this variant for variable currents, the Ampere-Maxwell law. It basically says an electric field that moves in space creates a magnetic field. Earlier in this video, we talked about Gauss's law for electric fields. But Gauss's law can be applied to any type of field, including magnetic fields. Suppose we take a bar magnet and look at the magnetic field it creates. Now, we will demarcate a Gaussian surface. The field lines in equal the field lines out. In fact, no matter where you place the Gaussian surface or how big you make it, the field lines in will always equal the field lines out. No exceptions. That's because magnetic fields are starkly different from electric fields. In electric fields, the field lines start on positive charges and end on negative charges. But in magnetic fields, they form continuous loops. So every field line that enters the Gaussian surface must leave it eventually. Expressed as an equation, we can say, for any Gaussian surface, the magnetic flux out always equals the magnetic flux in. Or, alternately, the net magnetic flux, that is, magnetic flux out minus magnetic flux in, always equals 0. This is Gauss's law for magnetic fields, and it forms the third of Maxwell's laws. The fourth of Maxwell's laws is the easiest of all. It's just Faraday lens. In its original context, we applied Faraday lens to loops of wire. Faraday lens says a wire that feels a changing magnetic flux will create a counterfield that opposes that change, and to do that, it will create a voltage and a current. Maxwell rephrased Faraday lens like this. If you assume the loop's area and orientation to be constant, then the magnetic field is the only thing changing, and in response to that, the coil would produce a counterfield, a current and a voltage. But if a voltage exists, that necessarily means that an electric field exists. So Maxwell's reformulation of Faraday lens equivalently says that a magnetic field that changes over time must create an electric field. At this point, you might be thinking that Maxwell just collected 4 existing laws, 3.5 of which were by other people. First, Gauss's law for electric fields, the electric flux entering a region of space, a Gaussian surface, equals the electric flux leaving that region unless the region contains a net charge. 2. Ampere-Maxwell. An electric field moving in space creates a magnetic field. 3. Gauss's law for magnetic fields. The magnetic flux entering a Gaussian surface always equals the magnetic flux leaving the Gaussian surface. No exceptions. And 4. Faraday lens. A magnetic field that changes in time creates an electric field. So you might wonder, what's the significance? Well, you probably noticed that there's a symmetry between laws 2 and 4. A moving electric field creates a magnetic field, and a changing magnetic field creates an electric field. So you might be wondering, can you have an electric field that creates a magnetic field, which in turn creates an electric field, which in turn creates a magnetic field, and so on forever? That's what Maxwell figured out by solving all 4 equations at the same time. That requires some differential equations, so I'll just jump to the punchline. When you solve the equations simultaneously, you get these differential equations. You may not have seen equations like this before. These are the equations for waves, like ripples in a pond. These equations say, for the electric field to sustainably create the magnetic field and vice versa, the two have to start at a point and ripple outwards in waves, just like ripples in a pond. Moreover, the electric wave and the magnetic wave have to be in sync with each other. Now, the outermost ripple in a pond is called the wave front, and the velocity of the wave front is actually part of this equation. Those two coefficients, epsilon 0, mu 0, that's equal to 1 over the square of the velocity. So let's calculate what the velocity of this electric and magnetic wave would be. Epsilon 0 is equal to 1 over 4 pi k, the constant from Coulomb's law. Since we know k and mu 0, we can plug those in and solve for velocity. 300 million meters per second. Look familiar? It's the speed of light. That's what light is. Light is an electromagnetic wave, a moving electric field, creating a changing magnetic field, creating a moving electric field, creating a changing magnetic field, spreading out in all directions like ripples in a pond. This is Maxwell's contribution. Scientists like simplicity. They like to explain the greatest number of phenomena with the fewest possible rules. Maxwell united the rules of electricity and magnetism and proved mathematically that they give rise to the rules of light and optics, all in just 4 equations that have never been improved upon to this day. To me, that makes Maxwell's laws not just a major breakthrough in our scientific understanding, but one of the greatest achievements of our species.